Okay, I want to take a look at some applications again. We're going to start actually with applications of matrices, and then later on we'll look at some applications of determinants. Um, and this was just kind of neat. I was just interested in it. Being able to send a coded message. Cryptology is this area. A cryptogram is a message that's written in a code. And this is a really cool thing if you think about it, and probably some of you know other ways to encode and encrypt messages. This is sort of at the basic level, but one way to start with is, to encode a message is to assign a number to each letter in the alphabet. Okay, and so then you replace the letters with the corresponding numbers. Okay, if you just did that, those are sort of codings is usually relatively easy to break. There's something in the newspaper I do a lot is called the cryptoquote, where they've done that. They've just replaced every letter, actually not with a number, but with another letter. That's another way you could do it. Assign different letters to different letters. So it kind of scrambles the message, but because you know the frequency of certain letters in words, and the way the words are formed, you can sometimes break that code pretty quickly. Okay, but we're going to do a little more than that. What we're going to do is we're going to take our message and break it up into 1 by n matrices, row matrices. Okay, so first of all, to encode it, to assign this, we'll use this scheme right here. We have numbers for each letter, and then we'll actually use 0 for a space, if you will. And you can use other numbers for punctuation or other needs that you might have. But we're going to write the uncoded, we'll call them uncoded matrices, of 1 by 3 in this example. Again, this value of n could be anything, which sort of adds to the level of being able to keep it from being broken, the code to be from being broken. So we're going to take this message, call me today, and we're going to break it up into groups of 3 letters. Okay, and for each letter then we'll assign the corresponding number. All right, so C is 3, A is 1, L is 12, and that gives me my first block. Okay, and then I've got continued over to the L at the end of call with a space, and then me. So L is 12, space is 0, M is 13, and so on. Hopefully you understand that process. So we do that. Notice at the end we end with just a Y, and we need to continue that 3 block, that 1 by 3 matrix, and so we just tag on two spaces at the end, so you can tag on zeros at the end. So now this is uncoded in the sense that fairly, if you have a long message, fairly easy to break in a lot of sense because of patterns and so on that you can see, and the frequency of certain letters that are used. But what we're going to do is we're now going to code it, and the way to encode it is we're going to choose an invertible n by n matrix. In this case our n is 3, so it's going to be a 3 by 3 matrix, so it has to be invertible. And we're going to multiply the uncoded row matrices on the right by this matrix. And so we're going to get a coded row matrix from that. So for example, with this message here is an invertible matrix. It is invertible, and we can find its inverse using, for instance, the inversion algorithm. And we're going to encode this message, call me today. So we take our first 1 by 3 block uncoded matrix and we multiply with A on the right. And notice that has to be because this is a 1 by 3 times a 3 by 3. You could do this as a column and multiply by A on the left in that case, but I just like to keep it as rows just because we generally write script in rows, in a sense, going left to right as opposed to columns going down. So we multiply and we get this row. This is now a coded matrix. Okay, and we do that for each block, right? So the 12, 0, 13 multiplied by A and get its output, and so on. We do that, and then we take this sequence and of blocks and put them all together. Okay, and this is our coded sequence. Now, real important here, we don't want to tell anyone who may understand that, hey, they might have encoded this with a 3 by 3 matrix because they've got 1 by 3 blocks here. We'll just take away the brackets and simply give the string of numbers, and that's our encoded message. We send that. So now, in order to break this code, you're going to have to, number one, find the matrix, but you're not going to know necessarily what size it is. Okay. I guess you can count the number of numbers up, and it would have to be a factor, really, of that number of numbers, if you will, coded numbers that you have in your message. But still, it's very difficult to break this, I would think. I don't know. Maybe you know better about how to break messages, but that's a pretty neat way to do it. Now, of course, to uncode this message, if you receive this, how are you going to be able to know what the message was? Well, here's the neat thing about it. If X is our coded row vector formed from the uncoded row vector Y, so remember we take the uncoded row vector Y, multiply by A on the right, and so X is our coded matrix. But since A is invertible, I can multiply both sides of this equation by A inverse on the right, right? Then regroup here, right? In other words, use the associative property of multiplication to write it this way. And we know what happens when we multiply A times A inverse. I get the identity. And of course, Y times the identity is just Y. And so you see, to recover, if you will, the uncoded row vector, we will multiply the coded vector by the inverse of A on the right. Okay. So for example, if I want to decode the message found in the example above, so here's our message, how do I decode it? Okay, well, first of all, I've got to know the encoding matrix. If I don't, I'm going to be in trouble. So certainly you got to share your encoding matrix, okay, A, and then hopefully your person can compute the inverse. Now, here, going from here to the inverse, of course, again, we could use the inversion algorithm for this. At this stage, though, it's fine to go and just use your calculator's inverse button. So don't forget how you can do that in the calculator. I won't actually do it, but this key right here, X neg to the inverse. This is the inverse key, right? So if you have a matrix there, it will compute the inverse of the matrix. And you might want to use the convert to fraction key, like there's some fractions in here. Remember, under math, there's that convert to fractions key. That's very helpful. So you can use technology to do the computation of the inverse matrix for this for these exercises. So what we do is we now take this block, and now I know, since A is 3 by 3, I know I need to break these up into 1 by 3 rows. So I take the first 3, negative 8, 11, 40, 45, multiply by the inverse on the right, and I get back, if you go back to the previous page, you'll see this is the original 1 by 3 block, uncoded, right? And then we do the next 3, negative 1, 1, 63, multiply it by inverse, and we get that. And we continue to do that for all our blocks until we get our decoded message. And then we go back to that alphabet structure. So there's sort of 2 levels of this. You have to know not only the inverse, or the matrix that is being used to, the invertible matrix that's being used to encode the message, but you also need to know this assignment as well. Okay, because we can have different assignments, I guess, if we want to. So this and the matrix are shared with the sender and the receiver of the message, and then they can send messages between each other. So now you can now send secret messages to one another, and hopefully not be intercepted, or if they are, they will be encoded and your message will be secure. Okay, so pretty cool. I really like that way of using matrices. Kind of neat. All right, so what I want to look at now is another application, if you will. Some of you may be familiar with this. This is an application of determinants, and it's known as Cramer's rule. And it's used to actually find the solution of a system that consists of n linear equations and n unknowns. So we have to have the same number of equations as unknowns. And furthermore, the coefficient matrix A here, right, its determinant is not 0. In other words, the coefficient matrix A, which is going to be square because we have n equations and n unknowns, it's n by n. Excuse me, that matrix has to be invertible. And in this case, we can know that the system has a unique solution. Of course, we know if A is invertible, that's true for any n by 1 vector B. The system AX equal B has exactly one solution. And this solution, here's Cramer's rule, is given this way. X of 1 is the determinant of this new matrix A sub 1 divided by the determinant of A. X sub 2 is the determinant of a matrix A sub 2 divided by the determinant of A, and so on. And what are these A sub 1, A sub 2 to A sub n? Well, A sub j is obtained by replacing the jth column of the matrix A with the entries in the matrix B, the constants matrix. So you simply, to find x of 1, you take the matrix A and you remove its first column and replace it with B. You replace it with that. That's what these are. And so you find the solution to the system by just finding two determinants and dividing. Okay. Now I'm going to prove this in just a minute to see why this works, but let's just say, first of all, Cramer's rule. How useful is it in practicality? Well, think again about an n by n matrix. We've got to find, first of all, the determinant of A, which is n by n, and how many computations is that in general if we do cofactor expansion? Do you remember? If I have an n by n matrix, there will be basically n factorial computations, because you've got for cofactor expansion along a row, you've got n cofactors that are n minus 1 by n minus 1, right? One less, and you have n of those, and for each of those n minus 1 matrices, you have n minus 1, n minus 2 by n minus 2 cofactors, and so on, right? So you go down. So for instance, in a 4 by 4 matrix, you have 4 3 by 3 cofactors, and each of those 3 by 3 matrices, to find their determinants, you will need 3 2 by 2, right, cofactors, and so on. So you've got 4 times 3 times 2, which is essentially 4 factorial. So very costly. And notice you don't have to do it just for the matrix A, but you have to do it for A sub 1, A sub 2 to A sub n. You've got n plus 1 determinants to find, and each one is n factorial. So not only is it just, it's not just n factorial, it's n plus 1 factorial. And so it gets to be very costly. So this is not a very efficient method, and it's not typically used. There may be one exception if you just have to find one particular unknown instead of finding all n. If you maybe just need to find x sub 2, then maybe it's not as costly. One of the main things of Cramer's rules, it just gives us a nice concrete closed formula, if you will, for the solution. Really different than doing Gaussian elimination or Gauss-Jordan elimination. Before giving a proof, let's prove this. Recall that we talked about this formula for the inverse of an n by n matrix, which is 1 over the determinant of A times the adjoint of A. And the adjoint of A was the transpose of the matrix of cofactors. So if I take the matrix of cofactors, which is here, this is simply what? For the first entry, I compute the cofactor and replace the entry with its cofactor. Same with every entry. I can replace it with its corresponding cofactor. I then take the transpose of that matrix, that's the adjoint, divide that basically by the scalar multiplied by the reciprocal of the determinant of A, I get the inverse. Now just talking about computing n by n or n squared cofactors, which each require n minus 1 factorial computations, you're talking about a lot of computation to do this formula. So this formula, again, not a very efficient way to compute an inverse. Inversion algorithm is much more efficient. But again, nice closed form way of expressing the inverse. And that's going to be helpful in solving or proving this theorem from Mr. Kramer. Okay. By the way, this is not the Kramer from the Seinfeld series, but a different Kramer. Of course, he's capital C as opposed to K, I believe. So at any rate, let's go ahead and prove this. All right. So basically, I want to look at solving the system as we said, AX equal B. A is n by n, and we know it's invertible, right? Those are the assumptions, right? That the determinant of A is not 0. So therefore, this system has exactly one solution, and we know what that solution is, right? X is A inverse times B. I mean, that's just multiply both sides of this by A inverse, and we know this is what we get, right? We've done this before. Again, A inverse is n by n, B is n by 1, and of course x is n by 1. We get, x1, x2, all the way to xn. And according to this formula, then, if I replace A inverse with this formula, this is 1 over the determinant of A times the adjoint of A times vector B. Again, adjunct of A being n by n. This is a scalar, and n is n by 1, of course, gives us the n by 1 vector x. Okay, but what I want to look at now, so this is an n by 1 column vector, and I want to look at an arbitrary entry. I want to look at x sub I. What's the ith entry? And here, maybe I should do x sub j, but I'm going to use x sub I, so that's counting the entry, so it's actually going down the row. So x sub 1 would be the entry in the first row, x sub 2 would be the entry in the second row, and so on. But because this is an n by 1 column. And what is this going to be equal to? Well, it's a scalar multiple, right? 1 over the determinant of A, and I'll just write this a little bit shorthand, determinant of A this way, right? That's also the determinant of A. And what do we have here? When I do this matrix multiplication, how do I compute the entry? It's the row dot the column, right? And there's only one column here, obviously, so I just take the first row of the adjoint of A times the column, I get the first entry. Second row times the column gives me second entry, and so on. So here I'm doing the ith row. Okay, the first row, notice here's the adjunct of A. The first row is C11, C21 to Cn1. You might say, wait a minute, 2,1, that's second row, first column normally, but why is that? Because remember, we took the transpose over here. So it's the cofactor C21. So that's the first row. Second row is C12, C22, all the way to Cn2. And so you can see that the ith row of this dotted with B is going to look like this. So the first entry in the matrix B is B1, and the first entry in the ith column, ith row of adjoint of A is C1I. So notice how this is going. If this is the first row, it's 1, 1, 2, 1, 3, 1, N1. If it's the second row, it's 1, 2, 2, 2. So the second number goes with the row, essentially. Do you see that? So the ith row here. The next entry is B sub 2, right, in the column here, times the second entry in the ith row of the adjoint of A. That's C 2I, yeah. So again, the second entry in the ith row. So remember, why is it not I2? Because we did that transpose here. And so on. That continues down till we get to the last entry in the vector B, which is B sub n times C n I. Okay, so let's just talk about this. What is this? This looks almost like cofactor expansion for the matrix A. Notice this is the cofactor in the first row ith column of the original matrix A, right? Not in the matrix of cofactors. First row ith column, second row ith column, third row ith column, nth row ith column. Okay, so this is going down the ith column of A. These are the cofactors along the ith column of A. And if I do a cofactor expansion along the ith column of A, I get the determinant of A. But the problem is, instead of having, what are we supposed to do? Multiply the entry. So this, if this was A1I here instead of B1, and if this was A2I instead of B2, and if this was ANI instead of BN, we would just have cofactor expansion. We would have the determinant of A here, if that were the case. It's almost like the ith column of A has been replaced with B, the vector B, right? We've replaced the ith column of A with the vector B here. Doesn't that sound familiar, right? This is actually the determinant of that A sub I. You remember that A sub I thing we talked about? A sub I is obtained by replacing the, of course I got A sub j here, the jth column of A with the entries of this matrix. Okay, so the this would be the determinant of A sub I. It's replacing the vector B, right, with the ith column of A and computing that determinant. It would look exactly like this. And so this is the determinant of A sub I. So the determinant of A sub I times this, we can then write more compactly this way, which is the proof, because that's what Cramer's rule says. That's exactly how you determine x sub I. If it's x sub 1, it's this determinant of A sub 1 over A. If it's x sub 2, it's determinant of A sub 2 over A. So there's the proof. Let's look at a easy application. So some of you have seen Cramer's rules before. Here's how we would proceed. This system of linear equations, what's the solution using Cramer's rule? So what would your support look like? We would simply, first of all, write out the matrices of interest here. The coefficient matrix A is going to be what? Let's pull out the coefficients. So pull off the coefficients from over here. Of course, matrix B, our constants, is that. And of course, X, I'll just say for the sake of argument here, is this right here. So let's take a look at those three matrices we got to compute. What's A sub 1? Remember what that was? Remove this column from matrix A and replace it with the vector B, 4, 3, 0. Everything else is the same. And then A sub 2, remove the second column and replace it with 4, 3, 0. And A sub 3, oops, 1, 2, 4. So first two columns are the same as for A, and then B is replaced in the third column. Okay. All right. So now, and here's what I would say with your calculator. As I said, don't use the inversion algorithm to find, don't use cofactor expansion to find the determinant. I mean, you can if you want practice, but that's fine. But with a calculator, we can find these determinants, right? And I find that the determinant of A is negative 11. The determinant of A sub 1 is negative 15. The determinant of A sub 2 is 3. And the determinant of A sub 3 is negative 20. So I mean, there obviously is some computation involved in that, but to see how this works, we do that. And now it's just simple to write out the solution. According to Cramer's rule, here is x sub 1, which is the determinant of A sub 1, divided by the determinant of A, which simplifies down to positive, right? 15/11 negative divided by negative. So there's our x sub 1, already done. X sub 2, and we'll just finish this out. 3 divided by negative 11, so that's negative 3/11. And finally, x sub 3 is equal to negative 20 divided by negative 11, or positive 20/11. And so there's our solution, and that's how it works. And you can see how that's very nice. Of course, we're using technology to speed us along a little bit because there is some computational cost with these determinants, as we've said. But this is a nice little method. Okay, again, mostly useful in proving other theorems and so on and so forth, because it's a very compact formula almost for the solution to the system. And of course, it is restricted to square systems. So if you have more equations than unknowns, or vice versa, or if your matrix A square but not invertible, then of course this method doesn't work. So it's not the savior, certainly not used really in a lot of application in terms of actually solving systems, but very nice and interesting result. Okay, so we'll stop here, and the next one I want to look at some geometry uses in the determinant, look at some interesting geometry uses.